Hello, my name is Tobias Langlotz. On behalf of my co-authors, I want to present our paper on a design space for vision augmentations and augmented human perception using digital eyewear. This is a collaboration between the University of Otago and University of Copenhagen. So, what are vision augmentations? Vision augmentations are actually based on the idea to replace traditional classes. Traditional classes we know for centuries. In fact, this is a painting from the 16th centuries that showed classes as we know them from nowadays, and they pretty much look the same. They have a static lens, and using that static lens, we somehow can change the appearance of the real world. For example, we can refract light rays differently so that they create a sharp image, or we can darken the glass to filter the incoming light. The general idea of vision augmentations, sometimes also referred to computational classes, is to now replace the static lenses with actually computerized versions or programmable optics. And the idea is here that with these programmable optics, we can change the appearance or our perception of the environment in quite dramatically different ways and extend what we can do. And over the time, we have seen lots of applications for these vision augmentations. And we usually would group them into two big areas. One is applications that compensate for visual impairments. And you see here on the right-hand side one of the example. So this is 4C that changed, for example, through edge enhancement, magnification, or even reversing the intensities. It changed our perception of the real world to, for example, address low vision. Or here's another example of our own group where we changed color perception to address color vision deficiency or color blindness. So the idea is when you wear these certain glasses, then we change the colors and reveal colors that are otherwise hard to distinguish. But beside these applications in compensating visual impairments, we also see applications that extend visual abilities. So here's one of the many examples. It's from Yuta Ito's group, and this is their work on the Plaschian vision. So here, actually, what they allowed is with classes, they allowed us to see movements in a different way and even give us that motion prediction. So we see actually where the ball will move or the trajectory of the ball ahead of time. Yeah. Sometimes these applications of extending visual abilities are also termed or have the goal of creating superhuman vision. All these approaches is common that you use different forms of technologies. Of course, there are traditional optics. I already talked about that and most of us know them, but there's also the area of computational optics. So there's some computer-controlled optics, for example, focus tunable lenses, or for example, these filters, as you can see on the right-hand side, that can be controlled on a per pixel level and allow incoming light control on a per pixel level. But most commonly, we see vision augmentations that use devices and technologies that we know from augmented or virtual reality. For example, optical see-through head-mounted displays that are repurposed, or video see-through head-mounted displays, like, for example, traditionally the HTC Vive or Oculus Quest, and in the future, probably also the Apple Vision Pro, that capture the environment with integrated cameras and then allow us to display that modified camera stream on the integrated display. Overall, we would state, or we would define, that vision augmentations are an extension of visual perceptual abilities to extents or domains where technical sensors and optical devices exist that exceed human capabilities due to no inferior or impaired perception. And what we see in this work on vision augmentations is that they're highly interdisciplinary, really spanning accessibility, human-computer interaction, graphics, visualization techniques, but also, of course, ophthalmology and optometry, to only name a few. We also see, because of that there's quite a different vocabulary and terminologies used. And early works have identified that there's a limited number of comparative studies, for example, for color vision deficiency, comparing different methods for doing vision augmentations. And this also is a result from that we have quite a limited insight into the core building blocks for vision augmentations. So not necessarily we know actually how can we actually modulate vision. We only see selective applications of some techniques. And this is the gap that we generally want to address with our work on a design space for vision augmentations. So design space are relatively commonly used in human-computer interaction, but also in other fields. to really portray and visualize a solution space for a given problem. So this is a relatively known example, a known work on a morphological analysis of a design space for input devices. And here they really portrayed or visualized the design space for input devices. And they used a certain approach, which is called a morphological analysis, which is also one of the common approaches for creating a design space, which tries to map the different dimensions that span or form that solution space. And then once with this given design space, what you can do, as we see here, you can, for example, illustrate existing solutions, but you also can identify areas that are not covered. So areas in the solution space where no solutions have been identified. And then you can prototype solutions for later evaluation. That was exactly the same approach that we also wanted to take for our work. So we also used a morphological analysis. However, one of the key challenges or the key questions first is, what are your dimensions? We outlined in detail in our paper the pathway that we took, but at the end we agreed on having 2 dimensions, and this is the source visual domain and this is the target visual domain. Because that results from observation that most of the techniques, not most, all of the techniques in vision augmentations, they mapped somehow between certain visual cues to other visual cues. So and these visual cues, we didn't use the word cues because there's a certain notion attached to it that would not allow us to cover the full design space. We used the word visual domains, and we identified 6 key visual domains. That is the stimulus field. That's everything related to how much we see, so our field of view, but also the resolution and magnification. The focus domain, so everything related to focus or blur. Photoreception, so the colors and wavelength that we can perceive, but also their intensities. The temporal domain, which relates to motion perception, but also flicker perception. Binocular vision, that perceive to effects that results from binocular vision, so the effect that we see with 2 eyes. So for example, virgin and stereopsis are here certainly key elements. And finally, patterns. So these are geometric primitives that we perceive, for example, like shape, icons, text, or hatchings. And we see that our target visual domain is composed of the same visual domains. And they span up our design space. So in our design space, for example, is then composed of these many cells, and solutions in the design space sit in these cells, but could also actually sit in several cells at the same time. So for example, you could remap from photoperception to photoperception, but also to patterns, as we will see in a second. So let me give an example and start with a single example, with a mapping from photoperception to photoperception. So actually what we do here is we change our photoperception. So for example, certain colors, as illustrated here in our example of addressing color vision deficiency, we change them, for example, by changing the colors or by changing the intensities. But we still stay in the same visual domain, and we call this, if we stay in the same visual domain, a modulation, because we modulate the same visual domain. Another example here, where we map from photoreception to patterns. So the idea is here, this is a work from David Fletler, who has many contributions in the field of color vision deficiency. And this is a specific solution that mapped from photoreception to patterns. Here in the paper, they're called metas. That form some forms of hatching or shape and indicate the color. We call these, if we map from one domain into the next one, a transformation in our design space. So here are a couple of other examples. For example, a modulation of the stimulus field. So how much do we see? This is a work from Jason Olowski, and similar to the earlier work on addressing low vision, what we could do, for example, with a camera, we can focus closer and actually magnify a certain area. So we change just the stimulus field, and it's a modulation. But we can also give a different idea of the stimulus field by mapping it to patterns. This is the work from Ali Pelli, who addressed tunnel vision. And here what they did, they had the camera capturing a wider field of view that is perceivable, and they extracted edges and these low-level patterns, and then they compress that into the visible field of view or stimulus field. So you basically, it's almost like a double exposure. You see the real image, and you see the edges or shapes of a wider field of view. again, as an example for transformation. Another example for transformation, photoreception, and a remapping to binocular vision. So for example, you show a different color or different intensities to the left and to the right hand, to left and to the right eye. And by doing so, you can create a relatively salient effect for highlighting certain colors or certain aspects of your certain intensities. I will not go into detail. There are lots of more examples, but what can you do now with that, with the design space? First of all, you can generate insights, and we provide quite some detail in the paper, but on a high level, for example, you can map existing technologies into the design space. So for example, you can see here that traditional optics, not surprisingly, only cover a very small area in our design space and actually don't really express the wide range of solutions in our design space, because traditional optics, usually they can change the magnification. For example, they can change the refractive power, and to some extent they can change our photo reception because they can make certain areas darker, but they can't make that lighter, and they can't do it usually on a per pixel base. Yeah, so usually they just allow for modulations. Contrary to this, taking video see-through HMDs, and what they allow in our design space, we can see that they actually really reflect the diversity of existing solutions in our design space. That is because they completely decouple the wearer of the system from the reality, and everything is camera mediated. Because we have full control over the camera image, we can almost change everything. Yeah. We also detailed in our paper how optical see-through HMDs and computational optics sit in that design space. And let me just say, they're a bit more limited and have some shortcomings, but also have some advantages. We also outline in our paper, for example, existing solutions where they would sit in our design space, or specific applications, for example, those who address impaired perception, as well as those who address extending perception, or what they call superhuman vision. However, you can also use the design space and utilize it for generating new design alternatives. And in fact, this is one of the strong reasons for developing design spaces. So in our papers, we did this in quite some detail for two examples. And I just mainly want to talk about the first one. And this is, again, color perception or photoreception. As already said before, for example, you can remap it to patterns, as has been presented in the literature. So you can represent certain colors or intensity through patterns. You can change them and represent them through a different image in the left and right image, which creates certain effects. You can reflect them through certain temporal changes, or, as also indicated earlier, you can just change colors to certain rules, for example, change their intensities, or even change their color space. As part of this work, we also identified new solutions, for example, to just represent different colors or different intensities, for example, by a different amount of focus. Yeah, this effect is relatively weak here, but when you see it in HMD, it's relatively strong. Or you, for example, can magnify it differently. Yeah, so for example, certain colors here, the red is a bit magnified, becomes a bit larger, green becomes a bit smaller, which also creates a very strong effect. In the paper, we outline not just the modulation or the different solutions with respect to photoreception, but, for example, also the stimulus field, and we picked those both examples because they commonly addressed in the literature, so it was a bit harder to identify new solutions. As every work, our work has also some limitations, as you probably have seen. First of all, we only focus on the visual system. But of course, there are our human sensory system has also other senses that we have not considered. But we would argue that our design space can easily be extended with other sensory systems. It becomes larger, but then it would allow you, for example, also to consider a crosstalk between, or an augmentation of different systems. For example, that you augment taste with actually also by creating visual stimulus. Also, we did not evaluate our developed techniques. That was simply not the focus of our work. And finally, we understand this is only a first step towards a common terminology, but think it's an important step. So overall, in our paper, we give an overview on vision augmentations, the different application areas and the motivations. We introduce different technologies that have been used, but the core of our work is really the design space, and we provide much more detail in our work. Finally, we show in much more detail also how you can apply our design space, for example, for categorization, but also use it for the generation of new design alternatives. That ends my talks. I want to thank you. And again, I refer to the paper for details. And I want to acknowledge our funder of this work. That's the Marston Fund from the Royal Society, New Zealand. Thanks a lot.